Today we are going to be focusing on our units of ppm and ppb. This continues our learning objective for applying concepts of mass percent, volume percent, ppm, and bpm. If we look at the definitions of ppm and ppb, then we can see that they are pretty similar to our mass percent composition. For mass percent composition, we had mass solute divided by mass solution, and then we multiplied by 100. But for ppm and ppb, we are going to be multiplying by 1,000,000 and by 1,000,000,000 instead of by 100. So these are our new multiplication factors for these units. The ppm and ppb are used to express concentrations when you have a very, very, very small amount of solute in your solvent. These are very analogous to our mass percent composition. So for instance, if you saw a mass percent composition as 20%, then you could translate this into a conversion factor by knowing that percent means out of 100, like divided by 100. So 20% means 20 out of 100. You can have whatever unit prefix you want in front of that mass as long as the prefixes match. And so that could be milligrams out of milligrams, that could be kilograms out of kilograms. It doesn't matter as long as the units match. If you saw a unit of 20 ppm, then that translates to out of 1,000,000 instead of out of 100. So 20 ppm means 20 out of 1,000,000. You have to pick mass units that match. That's the key thing here. So you could have that be milligrams, milligrams. You could have that be kilograms, kilograms. It doesn't matter as long as the units match. And then same thing here for 20 ppb. 20 ppb means out of 1,000,000,000. And so 20 ppb, 20 out of 1,000,000,000, and then same thing. As long as your units match, then you're good. Let's do an example problem. Here it says if there are 0.521 milligrams of arsenic in this many grams of solution, what is the concentration of arsenic in ppm? So I am asked to find ppm. And I am given my mass of solute and I am given my mass of solution. So let's look at what the definition of ppm is. ppm is equal to my mass of solute divided by my mass solution. And then there's a multiplication factor of 10 to the 6th. So let's see. I can set that up by plugging in my values. And then I know that I multiply by 10 to the 6th. But my units don't match right now. I need them to match before I type this into my calculator. So I'll write that. Make units match. One of the easiest, laziest ways of making them match is to just replace that prefix letter with its scientific notation equivalent. So I know that M stands for 10 to the minus 3. So I can just plug that in. wherever I see the letter. I'm going to just leave a space so I can shove that in there. I'm going to use So I'm going to plug in my prefix letter for that. Now my units match. I have grams over grams. You have to remember to still include my 10 to the minus 6. Now that we have these exponents, I can simplify. I can just combine the 10 to the minus 3 and the 10 to the minus 6. So I can come down here and I can simplify it to 0.521 grams over 363 grams. When I combine these two exponents together, I can add the exponent, and that would turn into 10 to the positive third. Now I can type it into my calculator, and I get 1.43526 ppm. Now I need to check my significant figures. This has 3 sig figs. This has 3 sig figs. So I need to keep 3 significant figures. 1, 2, 3. And so that works out to 1.44. Remember, the rounding rule for 5s is that we got to make that last digit even. So that means we're going to round up. Now there are other equivalencies that will be the same as ppm and ppb. Some of those equivalencies are here. And this works out because the difference in the magnitude of the prefixes works out to 10 to the 6th. So on some resources online, they might report out these different units, such as a milligram per kilogram. That is equivalent to 1 ppb. Or a microgram per milliliter also works out to 1 ppm. In this EPA report, it talks about milligrams per liter, and that's the same as this 1 milligram per kilogram because they're assuming that 1 liter of water weighs 1 kilogram. That's based on the density of water. If your solution is extremely dilute, like these ppm and ppb units mean they're for very dilute solutions, then you can assume that the density of the solution is essentially the same as that of water, pure water, because there's just not very much solute in there. If you have a much greater concentration, then you can't make that assumption. But that's how they're switching between these random volume units, like those, and mass units. They're making an assumption about the density. Let's go through another example problem. So in this example problem, it says, according to the 2017 Clovis Water Quality Report, the drinking water has a chloride concentration of 4 parts per million. So I'm given parts per million, and so I'm going to pull that out, and I'm going to rewrite it in such a way where I can write it kind of like a conversion factor, because I'm given it in the problem. That means I must need to probably use it as a conversion factor at some point. So 4 ppm means 4 out of a million. And I want to find the mass of chloride ion concentration. So I'm going to write that up here so that I remember what I'm trying to find. And then it says in 1 cup of water. And so I'm given 1 cup of water. What mass is in 1 cup of water? And then I can assume the density of the tap water is grams per milliliter, 1 gram per milliliter. So let me think about how I can connect my units together to solve this problem. All right, so I'm given my 1 cup of water. So I can go from cup I can go from cup to milliliters, and I'll use that conversion given to me. From milliliters, I have my density, so I could use my density value to go from milliliters to grams. That would be my grams of solution, because that's the density of like the entire water thing. And so then this is grams of solution. This is grams of chloride, because that's my solute. So I can use my parts per million. That was my density there. I can use my parts per million to get into grams of chloride ion. So let's see. That is what I'm trying to find. Grams is a unit of mass. So I would be good there. So now we got our solution map planned out. Let's use it. So I can start with my 1 cup of water. I want to cancel out cups, and I want to get into milliliters. I know that 1 cup is equal to 236.588 milliliters. Next up, I want to go from milliliters to grams of solution. So I'm going to cancel out my milliliters, and then I'm going to go into grams. This is where I use my density, and so the 1.00 is attached to the grams. All right, and then next up, that's my grams of solution. So remember that that's grams of solution. I have to have my grams of solution down here. And I want to get my grams of solute. And so this is where I'm going to pull out my ppm. And so I'm going to pull my 4.0 in the numerator, and then I'm going to put my 10 to the 6th in the denominator. Now I'm going to, let's see, that should give me my final unit that I want. And so I can go ahead and calculate that. If I plug that into my calculator, I get 0.000946 grams. That's really tiny. So I could choose to convert this to milligrams. And if I do, then I could report my unit as 0.946 milligrams. It didn't specify in the question prompt what mass unit it wanted, and so I have my choice of either. Now I need to check my significant figures. This has 2 sig figs. This density has 3 sig figs. This 1.0 cup has 2 sig figs. So out of all of my sig figs, I need to keep 2. That's what the multiplication rule says. And so then I have 0.95 milligrams. All right, one last practice problem. Go ahead and pause the video and try to work this out on your own. Unpause the video when you are ready to continue. All right, let's go over this. It says PCBs, polychlorinated biphenyls, are organic molecules with varying amounts of chlorine. PCBs used to be used as coolant in electrical equipment. What is the concentration in ppb? So we're trying to find ppb of PCBs in a chemical spill if there are that many milligrams in that much soil. So we are given, this is our solute mass, and this is our solvent mass. So we are given 0.070 milligrams PCB. I'm going to just write solute next to that. And we are also given 4750 kilograms. And so that is my solvent. So this sounds like I'm just going to be using that definition of what ppb is because I'm asked to calculate it. So if I have my ppb definition written out, then that would be my mass of solute divided by my mass of solvent, and then I would be multiplying by 10 to the 9th. And so I have both the numerator and the denominator, so I can go ahead and plug those in. And then I'd be multiplying by 10 to the 9th. But my units don't match yet, and so I have to make sure that I make my units match. So again, I can take a kind of lazy approach in converting back to the base unit so that they match. And so I'm just going to leave a space for me to write that scientific notation exponent. That's a 4750. And then that m stands for times 10 to the minus third power. That k stands for 10 to the third power. Now my units match because I'm in the base unit. So now that my units match, I can go ahead and type this into the calculator. And once I type that into the calculator, I get 0.0147368. And that would be ppb. Let's see what my sig figs need to be. If I look at my sig figs in the original information, this has 2 sig figs, the 7 and the 0. And this one has 3 sig figs. There's no decimal at the end, so the 0 can't be counted. So 2 versus 3, based on that multiplication rule, I would need to keep 2. And so that would translate to 0.015 ppb.